about 1953 when a noted philosopher here at MIT named Hubert Dreyfus, wrote a paper about 1963 in which he alleged, had a subject, had a heading titled, "Computers Can't Play Chess." Of course, he was subsequently invited over to the Artificial Intelligence Laboratory to play the Greenblatt chess machine, and of course he lost. Whereupon Seymour Papert wrote a rebuttal to Dreyfus's famous paper, which had a subject heading, "Dreyfus Can't Play Chess Either." But in a strange sense, Dreyfus might have been right, and would have been right if he were to have said, "Computers can't play chess the way humans play chess yet." In any case, around about 1968, a chess master named David Levy bet noted founder of artificial intelligence, John McCarthy, that no computer would beat the world champion within 10 years. And 5 years later, McCarthy gave up because it had already become clear that no computer would win in a way that McCarthy wanted it to win, that is to say, by playing chess the way humans play chess. But then 20 years after that, in 1997, Deep Blue beat the world champion, and chess suddenly became uninteresting. But we're going to talk about games today because there are elements of gameplay that do model some of the things that go on in our head. And if they don't model things that go on in our head, they do model some kind of intelligence. And if we're to have a general understanding of what intelligence is all about, we have to understand that kind of intelligence too. So we'll start off by talking about various ways that we might design a computer program to play a game like chess. And we'll conclude by talking a little bit about what Deep Blue adds to the mix other than tremendous speed. So that's our agenda. By the end of the hour, you'll understand and be able to write your own Deep Blue if you feel like it. First, we want to talk about how it might be possible for a computer to play chess. And let's talk about several approaches that might be possible. Approach number one is that the machine might make a description of the board, same way a human would. Talk about pawn structure, king safety, whether it's a good time to castle, that sort of thing. So it would be analysis, and perhaps some strategy mixed up with some tactics. And all that would get mixed up and finally result in some kind of move. So if this is the game board, the move, the next thing to do would be determined by some process like that. And the trouble is, no one knows how to do it. And so in that sense, Dreyfus is right. None of the game-playing programs today know how to incorporate any of that kind of stuff. So since nobody knows how to do that, we can't talk about it, so we can talk about other ways, though, that we might try. For example, we could have if-then rules. How would that work? That would work this way. You look at the board, represented by this node here, and you say, well, if it's possible to move the queen pawn forward by one, then do that. So it doesn't do any evaluation of the board. It doesn't try anything. It just says, let me look at the board and select a move on that basis. So that would be a way of approaching a game situation like this. Here's the situation. Here are the possible moves, and one is selected on the basis of an if-then rule, like so. And nobody can make a very strong chess player that works like that. Curiously enough, someone has made a pretty good checkers playing program that works like that. Checks to see what moves are available on the board, ranks them, picks the highest one that's available. But in general, that's not a very good approach. It's not very powerful. You couldn't make well, when I say couldn't, it means I can't think of any way that you could make a strong chess playing program that way. So a third way to do this is to look ahead and evaluate. And what that means is you look ahead like so, you see all the possible consequences of moves, and you say, which of these board situations is best for me? So that would be an approach that comes in here like so and says, which one of those three situations is best? And to do that, we have to have some way of evaluating the situation, deciding which of those is best. Now I want to do a little brief aside, because I want to talk about the mechanisms that are popularly used to do that kind of evaluation. In the end, there are lots of features of the chess board. Let's call them F1, F2, and so on. And we might form some function of those features, and that overall is called the static value. So it's static because you're not exploring any consequences of what might happen. You're just looking at the board as it is, checking the king's safety, checking the pawn structure. Each of those produces a number, feeds into this function. Out comes a value, and that is a value of the board seen from your perspective. Now, normally, this function g is reduced to a linear polynomial. So in the end, the most popular kind of way of forming a static value is to take f1, multiply it times some constant c1, add c2, multiply it times f2, and that is a linear scoring polynomial. So we could use that function to produce numbers from each of these things and then pick the highest number, and that would be a way of playing the game. Actually, a scoring polynomial is a little bit more than we need, because all we really need is a method that looks at those three boards and says, I like this one best. It doesn't have to rank them. It doesn't have to give them numbers. All it has to do is say which one it likes best. So one way of doing that is to use a linear scoring polynomial, but it's not the only way of doing that. So that's number 2 and number 3. But now what else might we do? Well, if we reflect back on some of the searches we talked about, what's the base case against which everything else is compared? What's the way of doing search that doesn't require any intelligence, just brute force? We could use the British Museum algorithm and simply evaluate the entire tree of possibilities. I move, you move, I move, you move, all the way down to what? Maybe 100, 50 moves. You would do 50 things, I do 50 things. So before we can decide if that's a good idea or not, we probably ought to develop some vocabulary. So consider this tree of moves. There'll be some number of choices considered at each level, and there'll be some number of levels. So the standard language for this is to call this the branching factor. And in this particular case, b is equal to 3. This is the depth of the tree, and in this case, d is 2. So now that produces a certain number of terminal or leaf nodes. How many of those are there? Well, that's a pretty simple computation, right? It's just b to the d, right, Christopher? B to the d? So if you have b to the d at this level, you have 1. B to the d at this level, you have b. B to the d at this level, you have b squared. So b to the d in this particular case is 9. So now we can use this vocabulary that we've developed to talk about whether it's reasonable to just do the British Museum algorithm, be done with it, forget about chess and go home. Well, let's see. It's pretty deep down there. If we think about chess, and we think about a standard game which each person does 50 things, that gives a d of about 100. And if you think about the branching factor in chess, it's generally presumed to be, depending on the stage of the game and so on and so forth. It varies, but it might average around 14 or 15. If it were just 10, that would be 10 to the hundredth, right? But it's a little more than that because the branching factor is more than 10. So in the end, it looks like, according to Claude Shannon, there are about 10 to the 120th leaf nodes down there. And if you were going to do a British Museum treatment of this tree, you'd have to do 10 to the 120th static evaluations down there at the bottom, if you're going to see which one of the moves is best at the top. So is that a reasonable number? You know, it didn't used to seem practicable. It used to seem impossible. But now we've got cloud computing and everything, and maybe we could actually do that. Right? What do you think, Manasseh? Can you do that? Get enough computers going in the cloud? You're not sure? Should we work it out? Let's work it out. I need some help, especially from any of you who are studying cosmology. So we'll start with how many atoms are there in the universe? Volunteers? 10 to the... No. 10 to the 38th has been offered. That's way too low. Last time I looked, it was about 10 to the 80th atoms in the universe. The next thing I'd like to know is how many seconds are there in a year? It's a good number to have in your, memorized. And that number is approximately pi times 10 to the 7th. Okay? So how many nanoseconds in a second? That gives us 10 to the 9th. And at last, how many years are there in the history of the universe? What? She offers something on the order of 10 billion. Okay, maybe 14 billion. But we'll say 10 billion to make our calculation simple. So that's 10 to the 10th years. So if we add all that up, 80, 90 plus 16, that's 10 to the 106 years, 10 to the 106th nanoseconds in the history of the universe, multiplied times the number of atoms in the universe. So if all of the atoms in the universe were doing static evaluations at nanosecond speeds since the beginning of the Big Bang, would still be 14 orders of magnitude short. So it'd be a pretty good cloud. We'd have to harness together lots of universes to do it. So the British Museum algorithm is not going to work. No good. So what we're going to have to do is we're going to have to put some things together and hope for the best. So the fifth way is the way we're actually going to do it. And what we're going to do is we're going to look ahead, not just one level, but as far as possible. So we consider not only the situation that we've developed here, but we'll try to push that out as far as we can and look at these, look at the static values of the leaf nodes down here and somehow use that as a way of playing the game. So that is number 5, and number 4 is going all the way down there. And this, in the end, is all that we can do. This idea is multiply invented, most notably by Claude Shannon and also by Alan Turing, who I found out from a friend of mine spent a lot of lunchtime conversations. They spent a lot of lunchtime conversations talking with each other about how a computer might play chess against the future when there would be computers. So Donald Mickey and Alan Turing also invented this over lunch while they were taking some time off from cracking the German codes. Well, what is the method? I want to illustrate the method with the simplest possible tree. So we're going to have a branching factor of 2, not 14, and we're going to have a depth of 2, not something highly serious. So here's the game tree, and there are going to be some numbers down here at the bottom. And these are going to be the value of the board from the perspective of the player at the top. And let us say that the player at the top would like to drive the play as much as possible toward the big numbers. So we're going to call that player the maximizing player. He would like to get over here to the 8, because that's the biggest number. There's another player, his opponent, which we'll call the minimizing player, and he's hoping that the play will go down to the board situation that's as small as possible, because his view is the opposite of the maximizing player. All right, hence the name Minimax. But how does it work? Do you see which way the play is going to go? How would you decide which way the play is going to go? Well, it's not obvious at a glance. Do you see which way it's going to go? It's not obvious at a glance. But if we do more than a glance, if we look at the situation from the perspective of the minimizing player here at the middle level, it's pretty clear that if the minimizing player finds himself in that situation, he's going to choose to go that way. And so the value of this situation from the perspective of the minimizing player is 2. He'd never go over there to the 7. Similarly, if the minimizing player is over here with a choice between going toward a 1 or toward an 8, he'll obviously go toward a 1. And so the value of that board situation from the perspective of the minimizing player is 1. So now we've taken the scores down here at the bottom of the tree and we back them up 1 level. And you see how we can just keep doing this? Now the maximizing player can see that if he goes to the left, he gets a score of 2. If he goes to the right, he only gets a score of 1. So he's going to go to the left. And so overall then, the maximizing player is going to have a 2 as the perceived value of that situation there at the top. So that's the Minimax algorithm. It's very simple. You go down to the bottom of the tree, you compute static values, you back them up level by level, and then you decide where to go. And in this particular situation, the maximizer goes to the left and the minimizer goes to the left too, so the play ends up here, far short of the 8 that the maximizer wanted, and less than the 1 that the minimizer wanted. But this is an adversarial game. You're competing with each other, so you don't expect to get what you want. All right? So maybe we ought to see if we can make that work. There's a game tree. Do you see how it goes? Let's see if the system can figure it out. So there it goes, crawling its way through the tree. This is a branching factor of 2, just like our sample, but now 4 levels. You can see that it's got quite a lot of work to do. It's 2 to the what? 2 to the 4th. That's 1, 2, 3, 4. 2 to the 4th. 16 static evaluations to do. So it found the answer, but it's a lot of work. we could get a new tree and restart it, maybe speed it up. And it goes down that way, get a new tree. Those are just random numbers, so each time it's going to find a different path through the tree according to the numbers that it's generated. Now 16 isn't bad, but if you get down there around 10 levels deep and your branching factor is 14, well, we know those numbers get pretty bad because the number of static evaluations due down there at the bottom goes as b to the d. That's exponential. And time has shown that if you get down about 7 or 8 levels, you're a jerk. And if you get down about 15 or 16 levels, you beat the world champion. So you'd like to get as far down in the tree as possible, because when you get as far down into the tree as possible, what happens is that these crude measures of board quality begin to clarify. And in fact, when you get far enough, the only thing that really counts is piece count, one of those features. So if you get far enough, piece count and a few other things will give you a pretty good idea of what to do, if you get far enough. But getting far enough can be a problem. So we want to do everything we can to get as far as possible. We want to pull out every trick we can find to get as far as possible. Now, you remember when we talked about branch and bound, we knew that there were some things we could do that would cut off whole portions of the search tree. And so what we'd like to do is find something analogous to this world of games that will cut off whole portions of the search tree so we don't have to look at those static values. So what I want to do is I want to come back and redo this thing. But this time I'm going to compute the static values one at a time. I've got the same structure in the tree. And just as before, I'm going to assume that the top player wants to go toward the maximum values and the next player wants to go toward the minimum values. But none of the static values have been computed yet. So I better start computing them. That's the first one I find, 2. Now, as soon as I see that 2, as soon as the minimizer sees that 2, the minimizer knows that the value of this node can't be any greater than 2, because he'll always choose to go down this way if this branch produces a bigger number. So we can say that the minimizer is assured already that a score there will be less than 2, equal to or less than 2. So now we go over and compute the next number. There's a 7. Now he knows it's exactly equal to 2 because he'll never go down toward the 7. As soon as the minimizer says equal to 2, the maximizer says, okay, I can do equal to or greater than 2. All right? 1. Minimizer says equal to or less than 1. Now what? Compare those two numbers. The maximizer knows that if he goes down here, he can't do better than 1. But he already knows if he goes over here, he can get a 2. So it's as if this branch doesn't even exist, because the maximizer would never choose to go down there. And so you have to see that, because this is the important essence of the notion of the alpha-beta algorithm, which is a layering on top of Minimax that cuts off large sections of the search tree. So one more time. We've developed the situation so we know that the maximizer gets a 2 going down to the left, and he sees that if he goes down to the right, he can't do better than 1, so he says to himself, it's as if that branch doesn't exist, and the overall score is 2, and it doesn't matter what that static value is. It can be 8, as it was. It can be plus 1,000. It doesn't matter. It can be minus 1,000. Or it could be plus infinity or minus infinity. It doesn't matter, because the maximizer will always go the other way. So that's the alpha-beta algorithm. Can you guess why it's called the alpha-beta algorithm? Well, because in the algorithm there are 2 parameters, alpha and beta. So it's important to understand alpha-beta is not an alternative to Minimax. It's Minimax with a flourish. It's something layered on top. Like we layered things on top of branch and bound to make it more efficient. We layer stuff on top of Minimax to make it more efficient. And you say to me, well, that's a pretty easy example, and it is, so let's try a little bit more complex one. This is just to see if I could do it without screwing up. All right? The reason I do one this complex is not just to show how tough I am in front of a large audience, but rather there are certain points of interest that only occur in a tree of depth 4 or greater. That's the reason for this example. But work with me, and let's see if we can work our way through it. What I'm going to do is I'll circle the numbers that we actually have to compute. So we actually have to compute 8. And as soon as we do that, the minimizer knows that that node is going to have a score of equal to or less than 8 without looking at anything else. Then he looks at 7. So that's equal to 7, because the minimizer will clearly go to the right. As soon as that is determined, then the maximizer knows that the score here is equal to or greater than 8. Now we evaluate the 3. The minimizer knows equal to or less than 3. Oh, sorry. Minimizer 7, yeah. Okay, now what happens? Well, let's see. The maximizer gets a 7 going that way. Can't do better than 3 going that way. So we got another one of these cutoff situations. It's as if this branch doesn't even exist. So this static evaluation need not be made. And now we know that that's not merely equal to or greater than 7, but exactly equal to 7. And we can push that number back up. So that becomes equal to or less than 7. Okay, you with me so far? Let's get over on the other side of the tree as quickly as possible. So there's a 9, equal to or less than 9. 8, equal to 8. Push the 8 up, equal to or greater than 8. So the minimizer can go down this way and get a 7. We'll certainly never go that way, where the maximizer can get an 8. So once again, we've got a cutoff, and it's as if this branch didn't exist, and that means that these static evaluations don't have to be made, and this value is now exactly 7. But there's one more thing to note here, and that is that not only do we not have to make these static evaluations down here, but we don't even have to generate these moves. So we save 2 ways, both on static evaluation and on move generation. So this is a real winner, this alpha beta thing, because it saves an enormous amount of computation. Well, we're on the way now. The maximizer up here is guaranteed equal to or greater than 7. Has anybody found the winning move yet? Is it to the left? I don't know. We better keep going because we don't want to trust any oracles. So let's see. There's a 1. We've calculated that. The minimizer can be guaranteed equal to or less than 1 at that particular point. Think about that for a while. At the top, the maximizer knows he can go left and get a 7. The minimizer, if the play ever gets here, can ensure that he's going to drive the situation to a board number that's 1. So the question is, would the maximizer ever permit that to happen? And the answer is surely not. So over here, in the development of this side of the tree, we're always comparing numbers at adjacent levels in the tree. But here's a situation where we're comparing numbers that are separated from each other in the tree, and we've still concluded that no further examination of this node makes any sense at all. This is called deep cutoff. And that means that this whole branch here might as well not exist, and we won't have to compute that static value. All right? So it looks, you have this stare of disbelief, which is perfectly normal. I have to reconvince myself every time that this actually works. But when you think your way through it, it is clear that these computations that I've X'd out don't have to be made. So let's carry on and see if we can complete this. Equal to or less than 8, equal to 8, equal to 8, because the other branch doesn't even exist, equal to or less than 8. And we compare these two numbers. Do we keep going? Yes, we keep going, because maybe the maximizer can go to the right and actually get to that 8. So we have to go over here and keep working away. There's a 9, equal to or less than 9. Another 9, equal to 9. Push that number up, equal to or greater than 9. Let's see, minimizer gets an 8 going this way. The maximizer is ensured of getting a 9 going that way. So once again, we've got a cutoff situation. It's as if this doesn't exist. Those static evaluations are not made. This move generation is not made, and computation is saved. All right? So let's see if we can do better on this very example by using this alpha beta idea. I'll slow it down a little bit. We'll change the search type to Minimax with alpha beta. We see 2 numbers on each of those nodes now. Guess what they're called? We already know, right? They're alpha and beta. So what's going to happen as the algorithm proceeds through the tree is that those numbers are going to shrink wrap themselves around the situation. So we'll start that up. So 2 static evaluations were not made. Let's try a new tree. Two different ones were not made. A new tree. Yet still again, 2 different ones not made. Let's see what happens when we use the classroom example, the one I did up there. Let's make sure that I didn't screw it up. Slow that down to 1. Phew, same answer. So you probably didn't realize it at the start. Who could? But in fact, the play goes down that way, over this way, down that way, and ultimately to the 8, which is not the biggest number, and it's not the smallest number. It's the compromise number that's arrived at in virtue of the fact that this is an adversarial situation. So you say to me, how much energy, how much work do you actually save by doing this? Well, it is the case that in the optimal situation, if everything is ordered right, if God has come down and arranged your tree in just the right way, then the approximate amount of work you need to do, the approximate number of static evaluations performed, is approximately equal to 2 times b to the d over 2. We don't care about this 2. We care a whole lot about that 2. So that's the amount of work that's done. It's b to the d over 2 instead of b to the d. What's that mean? Suppose that without this idea, I can go down 7 levels. How far can I go down with this idea? 14 levels. So it's the difference between a jerk and a world champion. So that, however, is only in the optimal case when God has arranged things just right. But in practical situations, practical game situations, it appears to be the case experimentally that the actual number is close to this approximation for optimal arrangements. So you would never not want to use alpha beta. Saves an amazing amount of time. You can look at it another way. Suppose you go down to the same number of levels, how much less work do you have to do? Well, quite a bit. The square root this month, right? So another way of looking at how it works. So we could go home at this point, except for one problem, and that is that we pretended that the branching factor is always the same. But in fact, the branching factor will vary with the game state and it will vary with the game. So you can calculate how much computing you can do in 2 minutes or however much time you have for an average move. And then you can say, how deep can I go? And you won't know for sure because it depends on the game. So in the early days of game playing programs, the game playing program left a lot of computation on the table because it would make a decision in 3 seconds, and it might have made a much different move if it used all the computation it had available. Alternatively, it might be grinding away, and after 2 minutes was consumed, it had no move and just did something random. So that's not very good. But that's what early game playing programs did because no one knew how deep they could go. So let's have a look at the situation here and say, well, here's a game tree. It's a binary game tree. That's level 0. That's level 1. This is level D minus 1. And this is level D. So down here, you have a situation that looks like this. And I've left all of the game tree out in between. So how many leaf nodes are there down here? B to the D, right? Oh, I'm going to forget about alpha beta for a moment. As we did when we looked at some of those optimal searches, we're going to add these things one at a time. So forget about alpha beta. Assume we're just doing straight minimax. In that case, we would have to calculate all these static values down here at the bottom, and there are B to the D of those. How many are there at this next level up? Well, that must be B to the D minus 1. How many fewer nodes are there at the second to the last, the penultimate level, relative to the final level? Well, 1 over B, right? So if I'm concerned about not getting all the way through these calculations at the D level, I can give myself an insurance policy by calculating out what the answer would be if I only went down to the D minus 1th level. All right, see how you get that insurance policy? It only costs me, let's say the branching factor is 10. How much does that insurance policy cost me? 10% of my computation. Because I can do this calculation and have a move in hand here at level D minus 1 for only 1/10 amount of the computation that's required to figure out what I would do if I go all the way down to the Dth level. Okay, is that clear? So this idea is extremely important in its general form, but we haven't quite got there yet, because what if the branching factor turns out to be really big and we can't get through this level either? What should we do to make sure that we still have a good move? Right, we can do it at the B minus 2 level. So that would be up here, and at that level, the amount of computation would be B to the D minus 2. So now we've added 10% plus 10% of that, and our knee jerk is beginning to form, right? What are we going to do in the end to make sure that no matter what, we've got to move? We're going to, what's that, Christopher? Start from the very first level and give ourselves an insurance policy for every level we try to calculate. But that might be real costly. So we better figure out if this is going to be too big of an expense to bear. So let's see, if we do what Christopher suggests, then the amount of computation we need in our insurance policy is going to be equal to 1. We're going to do it up here at this level too, even though we don't need it, just to make everything work out easy. 1 plus B, that's getting our insurance policy down here at this first level. And we're going to add B squared all the way down to B to the D minus 1. So that's how much we're going to spend getting an insurance policy at every level. What's the sum of that? High school algebra, right? Let's just do it for fun. Oh, unfortunate choice of variable names. BS is equal to, well, we're going to multiply all those by B. Okay? Now we'll subtract the first one from the second one. Which tells us that the amount of calculation needed for our insurance policy is equal to B to the D minus 1 over B minus 1. Is that a big number? We can do a little algebra on that and say that B to the D is a huge number, so that minus 1 doesn't count. And B is probably 10 to 15, so B minus 1 is essentially equal to B. So that's approximately equal to b to the d minus 1. So with an approximation factored in, the amount it takes us to, amount of computation needed to do insurance policy at every level is not much different from the amount of computation needs to get insurance policy at just one level, the penultimate one. So this idea is called progressive deepening. And now we can visit our gold star idea list and see how these things match up with that. First of all, the dead horse principle comes to the fore when we talk about alpha beta, because we note with alpha beta that we can get rid of a whole lot of the tree and not do static evaluation, not even do move generation. That's the dead horse we don't want to beat. There's no point in doing that calculation because it can't figure into the answer. The development of the progressive deepening idea I like to think of as in terms of the martial arts principle. We're using the enemy's characteristics against them. Because of this exponential blow-up, we have exactly the right characteristics to have a move available at every level as an insurance policy against not getting through the next level. And finally, this whole idea of progressive deepening can be viewed as a prime example of what we like to call anytime algorithms that always have an answer ready to go as soon as an answer is demanded. So as soon as that clock runs out at 2 minutes, some answer is available. It'll be the best one that the system can compute in the time available given the characteristics of the game tree as it's developed so far. So there are other kinds of anytime algorithms. This is an example of one. So that's how all game playing programs work. Minimax plus alpha beta plus progressive deepening. Christopher, is alpha beta an alternative to Minimax?
No.
No, it's not. It's something you layer on top of Minimax. Does alpha beta give you a different answer from Minimax?
No. No, it doesn't.
Let's see everybody shake their head one way or the other. It does not give you an answer different from Minimax. That's right. It gives you exactly the same answer, not a different answer. It's a speed up. It's not an approximation. It's a speed up. It cuts off lots of the tree. It's dead horse principle at work. Okay? You got a question, Christopher?
Yeah. Along the lines of progressively computing the best result, is it possible to almost keep a temporary value of the values you compute along each node of the tree, and then instead?
Oh, an excellent suggestion. In fact, Christopher has just, I think, if I can jump ahead a couple of steps, I think Christopher has reinvented a very important idea. Progressive deepening not only ensures that you get a better answer, progressive deepening not only ensures you have an answer at any time, it actually improves the performance of alpha beta when you layer alpha beta on top of it. Because these values that are calculated at intermediate parts of the tree are used to reorder the nodes under the tree so as to give you maximum alpha beta cutoff. I think that's what you said, Christopher. But if it isn't, we'll talk about your idea after class.
Sure.
So this is what every game playing program does. So how is Deep Blue different? Not much. So Deep Blue, as of 1997, did about 200 million static evaluations per second. And it went down, using alpha beta, it went down about 14, 15, 16 levels. So Deep Blue was Minimax plus alpha beta plus progressive deepening plus a whole lot of parallel computing plus an opening book plus special purpose stuff for the end game plus perhaps the most important thing, uneven tree development. So far, we've pretended that the tree always goes out in an even way to a fixed level. But there's no particular reason why that has to be so. Some situation down at the bottom of the tree may be particularly dynamic. In the very next move, you might be able to capture the opponent's queen. So in circumstances like that, you want to blow out a little extra search. So eventually you get to the idea that there's no particular reason to have the search go down to a fixed level, but instead you can develop the tree in a way that gives you the most confidence that your backed up numbers are correct. And so that's the most important of the extra flourishes added by Deep Blue when it beat Kasparov in 1997. And now we can come back and say, well, you understand Deep Blue, but is this a model of anything that goes on in our own heads? Is this a model of any kind of human intelligence, or is it a different kind of intelligence? And the answer is mixed, right? Because we're often in situations where we are playing a game. We're competing with another manufacturer. We have to think what the other manufacturer will do in response to what we do, and down several levels. On the other hand, is going down 14 levels what human chess players do when they win the world championship? Doesn't seem even to them like that's even a remote possibility. They have to do something different because they don't have that kind of computational horsepower. This is doing computation in the same way that a bulldozer processes gravel. It's substituting raw power for sophistication. So when a human chess master plays the game, they have a great deal of chess knowledge in their head and they recognize patterns. There are famous experiments, by the way, that demonstrate this in the following way. Show a chessboard to a chess master and ask them to memorize it. They're very good at that as long as it's a legitimate chessboard. If the pieces are placed randomly, they're no good at it at all. So it's very clear that they've developed a repertoire of chess knowledge that makes it possible for them to recognize situations and play the game much more like number one up there. So Deep Blue is manifesting some kind of intelligence, but it's not our intelligence, it's bulldozer intelligence. So it's important to understand that kind of intelligence too, but it's not necessarily the same kind of intelligence that we have in our own head. So that concludes what we're going to do today. And as you know, on Wednesday we have a celebration of learning, which is familiar to you if you've taken 3091. And therefore, I will see you on Wednesday. All of you, I imagine.